Okay, so we're going to have a look at this higher tier paper, and I'm going to go through some of the answers, well, all the answers, and at any point you can pause and have a look at the answers that I've got. You can rewind. I'm going to try and put a little bit of explanation between why the answers are as they are, and maybe some pointers on how to answer some of these questions. Okay, so the first one here is looking at, it's always helpful to read the blurb to begin with for the setting. And so we're reacting these metals with hydrochloric acid. So what's the order of decreasing activity? So basically the most reactive to the least reactive. So if we have a look, we can see the number of bubbles will tell us how reactive something is. So this is the most reactive. And looking at these, this has got no bubbles at all, so that's going to be the least reactive. So then we look at these two and we can see that this has got more bubbles than that, so that would be 2 and 3. So the order is calcium, magnesium, zinc and copper, which is the last choice on here. So nice little introductory question. So if we have a look at 1.2, we need to make a fair comparison between the reactivity of the metal. So this is asking for variables. So what two variables must you keep constant? So we're looking at control variables. So things that you need to keep constant, so you get a fair comparison, is use the same mass of the metal. So you can say the mass, weight is acceptable. There's a number here. I only need 2 of these. You could say you want the surface area of the metal to be the same. So basically, if you're going to use metal particles, you want to be using metal particles for everything. If you're using metal strip, you need to use metal strip for everything. So the surface area needs to be the same. The concentration of the acid, you don't want to use different concentrations of the acid, you want to keep the same. And volume of the acid. These are usually 2 nice ones that go hand in hand whenever you do control variables. Temperature of the acid as well, so you want to keep the temperature the same. So any 2 out of those is fine. It's wanting to know what the independent variable is. Well, you're comparing different metals, so it's the type of metal or different metals or different elements that would get you that mark there. 1.4, you need to predict the reactivity of beryllium compared to magnesium. So we're in group 2 here. So beryllium is at the top of group 2, magnesium is underneath it, calcium is further down. And we know as we go down metal groups, group 1 and group 2, the reactivity increases. So there's a number of answers we can do here. So we can say we have to compare beryllium to magnesium. So I need you to have lesser, fewer, more or less. I need that comparison. So beryllium is less reactive than magnesium because it's got a greater attraction between the nucleus and the outer electrons, so that means the outer electrons are harder to lose. So anything about reactivity is about electron transfer or electron movement. So chemical reactions is all about electron movement. So if those electrons are harder to lose, then the reaction is going to be slower. The other thing you could have said is that beryllium is higher up in the group than magnesium, so the reactivity increases as you go down the group. That would also have given you the mark, or marks. There's 2 marks there. 1.5, a solution of hydrochloric acid contains 3.2 grams of hydrogen chloride in 50 centimeters cubed. Calculate the concentration of hydrogen chloride. Concentration is just another word for density, so like density of a liquid. So we can measure density as grams, so it's grams per unit volume, or we do tend to use at higher tier moles per unit volume, but we're looking at grams, and it does say in grams per decimeter cubed. So there is a little pointer there. You've got to work out grams per decimeter cubed. You've been given 50 centimeters cubed, so to convert that to decimeters cubed, you need to divide it by 1,000. 1,000 centimeters cubed is 1 decimeter cubed. So that will give you 0.05. So you get 1 mark for using 0.05. If you get the right expression, grams divided by volume, which I have here, 3.2 divided by 0.05, you get another mark for doing grams divided by volume. And then if you get 64, you will get the answer, the full 3 marks. Okay, so that would be a nice little 3-mark question, but do use pointers in the question. So units is always a good one, and you can always look at units at the end as well to work out what you need to find out. Okay, so let's have a look at question 2. It wants the state symbol for ammonium nitrate, not the formula, the state symbol. And the state is it a gas, is it a liquid, or is it a solid? And this is aqueous, it's a solution. So a solution is AQ. Okay, so we've got 4 state symbols: gas, liquid, solid, and a solution is AQ, which means aqueous. 2.2, what's the formula of nitric acid? If you don't know, nitric acid's got a nitrogen in it, so you can look down here and cross off what doesn't have a nitrogen, which is HCl and H2SO4, so it's not those two. And an acid always has H plus, not OH minus. So which one of the two that you've got left has a H plus in it and not an OH minus? Well, we can see an OH minus, so it's not that one. It has to be this second one down. So by a process of elimination, if you don't know the formula, you can work it out. 2.3, it's wanting to know what the pH of the nitric acid is. We know it's an acid. So when we use universal indicator, that goes from red through orange, yellow, green to a turquoise, blue and purple. So it's acid in the red, yellow, orange region, and it's alkaline in the turquoise, blue, purple region. So nitric acid will be red, or you could have had orange or yellow because that's below 7, pH below 7. And the ammonia solution is going to be a pH above 7, so blue or purple, or shades of blue or shades of purple, lilac. That would have got you those marks as well. Okay, nice, straightforward question. Then looking at 2.4, it's just going further. Do you know the values? So it wants you to choose the correct pH value. So we can do a little bit of screening. So if it's ammonia, it's going to be in the blue end, so it's going to be greater than 7. If it's an acid, it's going to be less than 7. So which ones are greater than 7 here? Well, that's greater than 7. That one isn't. That one's 7, so it's not right. And that one's greater than 7. We need this one to be less than 7. Well, that's 7, so that's not right. That's 10. That's not right. 1 and 2. So there, that's right. So let's have a look. It can't be 7 and 1. It's 10 and 2. So there, by process of elimination, again, if you weren't sure, you could work it out. 2.5, calculate the percentage by mass of oxygen in ammonium nitrate. So it's given you the formula of ammonium nitrate. We have got 3 oxygens in ammonium nitrate. So we can work out what the mass of the oxygens are. It's 3 lots of oxygen, which is 3 times 16, that's 48. It's very kindly given us the mass of the ammonium nitrate, which is 80. So what percentage of that is oxygen? So 48 divided by 80 times 100 equals 60%. So you get a mark for working out 40%. You get a mark for doing the 48 over 80 times 100, and you get a mark for 60. So that's your 3 marks. Nice little 3-mark question. Okay, so this is a 6-mark question, and these, as long as you can bullet point these, so as long as you get all the work in, or the keywords in, you'll get a full 6 marks. So it says, describe a method to investigate how the temperature changes when different masses of ammonium nitrate are dissolved in water. So if you get some sort of method like this, you need to think independent variable, dependent variable, control variable. So even from here, how does the temperature change? So that's got to be a dependent variable when different masses are used. So that's got to be our independent. We are going to use different masses. Okay, and a control variable, we can work it out. So the independent variable, the thing that we change is the mass of ammonium nitrate. Now it is helpful if you choose different masses and show that you're going to use different masses. So this could be 1, 2, 3, 4, 5 grams, or as I've put here, 5, 10, 15, 20, 25 grams. As long as you show you're going to use different masses, you actually get a mark for that. You know, well, I say a mark, you get you are credited for it. The dependent variable, the thing that you're going to measure is the temperature change. So you're going to measure the start and end temperature of the reaction. So again, you get, I'm ticking it, but what that means is you're going to get a credit for it, so that it's going to, holistically, it's going to put you in a good light. And the control variable, these are the things that you are going to keep the same so that you get a fair comparison. And the volume of water. Now it could be any volume of water, 10 centimetres cubed, 20 centimetres cubed, 100 centimetres cubed. Just choose our value. I've chosen 20. So as long as my method, so I will get sort of credited for that. So as long as my method will give me a valid outcome, basically I can get proper results from it, then I will get full 6 marks. And I'm halfway there already just with the first part. So I'm going to put 20 centimetres cubed of water in a beaker and measure the start temperature. Now I forgot to put that, and as I was reading through I realised I hadn't put it. So I've put measure the start temperature. So, you know, as an examiner I go, yeah, I'm giving it a mark, I'm going to give it a tick. Yes, that's perfect. Add the, so I'm going to add the ammonium nitrate to the water. Yeah, that's perfect. I'm going to measure the maximum or minimum temperature achieved. So I'm going to measure a second temperature, so I can then get a temperature difference. Calculate the temperature difference and then repeat with a different mass of ammonium nitrate. Now that will give me a valid outcome. I will get valid results. I've stated here that I've got a control variable, I'm going to measure the temperature change, and I'm going to have different masses of ammonium. So that is a full 6 marks. I could have added, just to give it a bit of extra, that I'm going to stir the solid to dissolve. It's not going to change my results, but I could have added that. And I could also have added insulate the beaker to prevent heat loss. That would give me a good good results if I was looking for heat loss, if I didn't have any heat loss, but the results would be valid whether I did that or not. So anyway, what I've got there is full 6 marks. We want to be getting 6 marks on these questions, so sometimes just brainstorming it and putting bullet points is perfect. Okay, so let's move on to the next one. This is just looking at it straight away. I can see it's an exothermic process. That's immediately what comes to mind, because the product's energy is less than the reactant's energy, so this is definitely exothermic. Might want me to ask that. It says label the activation energy. So the activation energy I need to know is the difference between the reactants and the top of the curve, and I need to be careful when I do this. So I've put little lines there, and that is my arrow, and I've labelled the arrow activation energy. Okay, so as long as it's absolutely crystal clear what you're labelling, you'll get the mark. If it's arrows anywhere or doesn't look correct, you won't get the marks. And then I think on the other side it says label the energy change. We'll have a look. It says, oh, it doesn't say label the energy change. It says determine the overall energy change of the reaction between the hydrogen and oxygen. So I know that this is going to be the energy change, and it wants me to determine it. So I've got scales here, so I can read across and read across, and I'll find the difference. The difference is 500. So as long as I've got a difference, I'll get 1 mark, and as long as I come up with 500, I'll get another mark. I know it's exothermic, and I know that that value should be negative, but in this instance, it doesn't matter whether, if you put negative, that's fine. If you don't, it's not a problem. We're just calculating a difference here. Okay. So 3.3 is oxygen is in group 6. So it's got 6 electrons in its outside shell. It needs 2 electrons to make 8. So it's going to share 2 electrons with another oxygen. So it says draw the electrons in the outer energy levels. I know that each oxygen is going to contribute 2, so that it makes 8. And then we've got 1, 2, 3, 4, 5, 6. So we've got 6 electrons as crosses from the first oxygen, 6 electrons, 1, 2, 3, 4, 5, 6 as dots from the second oxygen, and each oxygen shares 2 electrons. So in this overlap, we'll get 2 crosses and 2 dots. So that's what I'm looking for. Okay, so you get a mark for the overlap, and then you get a mark for showing that we've got 2 pairs of electrons in each oxygen. Okay, now this is something that you will see every time, and this is something that completely throws candidates. And I don't know why, but you suddenly think that this 2 means you've got 2 OH bonds. Actually, what this 2 means is you've got 2 of these molecules. So I've drawn it. I mean, if I did 2H2O2, which is what this is, you'll know you've got 2 H2O2s. And if I did 2H2O, you know you've got 2 waters. Okay, so I've actually drawn it out in full. So 2 HOOH is HOOH, HOOH. I've got 2 of them, and I've got 2 waters, HOH, HOH, and 1 oxygen molecule, OO. Then what I've done in red, I've actually put the values of those bonds, those bond energies, on each of those bonds. Then I have calculated the total energy. So you can see I've kept the left side to the left, and I'm going to keep the right side to the right. So that's why I've put this little dotted line down here. And I've calculated the total energy to break all of those bonds. So I've got 1, 2, 3, 4 HO bonds. That's 4, 6, 4 times 4. And I've got 2 OO bonds. So 2 lots of 1, 3, 8. That gives me a total bond energy on the left hand side of 2128. I've done the same on the right hand side. So I've got 4 lots of 463. And I've got 1 496 bond. That should be 496. So the total on the right hand side is 2348. I don't think you can see that. That's a 4. 2348. Now to calculate the bond, the difference, the energy change, it's the left hand side take away the right hand side. So it's 2128 take away 2348, and that gives me a value of negative 220. If you get a positive 220, instead of 3 marks, you'll get 2 marks. You get 1 mark for showing these bond energies. If they're wrong, you get method mark. You get 1 mark for showing it's the left hand side total, take away the right hand side total, and then you get another mark for whatever the value of that is here. Okay, so you still get method marks, but do be aware of this. This will throw you each time. Make sure you write it out in full. Okay, so question number 4. This is talking about the periodic table. What order did scientists use to arrange the elements in the early periodic table? Well, they had absolutely no idea about electrons, about proton numbers, about atomic sizes, or even relative atomic masses. They only had the weight of the elements to go by, so they did it by atomic weight. And then in the early periodic table, what did Mendeleev do? Well, he left gaps, or he left spaces. So you can't say he waited for undiscovered elements, or he showed there was undiscovered elements. That's not part of it. He left gaps, or he left spaces. That's how he overcame elements being in the wrong groups. He left gaps, and he changed the order of the elements by grouping according to properties. So he was able to say, I think it's tellurium and iodine, he switched them around. He realized they were in the wrong group, so he switched them around based on their properties. So he changed the order and he based it on properties. So any one of those two would get you that 1 mark. Okay, so let's look at 4.4. We're looking at the boiling points of fluorine, chlorine and bromine, and we can see that they're becoming less negative. So if you draw yourself a little table where that's 0 and that is, say, minus 200, and this is plus 200, you can see that actually we're becoming more positive. We're starting to get an increase in boiling point, so the boiling point increases. So it says, explain why the boiling points are low. Well, they are low, and that's because the forces in between the molecules are quite weak. So we can say there are weak intermolecular forces of attraction between the molecules, or there are weak forces of attraction between the molecules. That would get you 1 mark. And because they're weak, it takes very little energy to break them. Okay, so there's your 2 marks. Weak intermolecular forces, and it takes very little energy to break them. So 2 marks means 2 facts, or 1 fact and explain because. Do a because statement. So 4.4, explain the trend in the boiling points. So as the molecules get larger as you go down group 7. So the forces between the molecules increase. So more energy is needed to break those forces. So the boiling point increases with relative atomic mass. Oops. Okay. And that's where this little scale here goes. So we've got fluorine down here. Then we've got chlorine. And then we've got bromine up here. So we can see that the boiling point increases. So when you're working with negatives, draw yourself a little table and you can work out whether the boiling point increases or decreases. Then you can get the correct terminology down here. Okay. If you need to, pause and have a look at that, or rewind for the explanation. So 4.5, explain why neon is unreactive. Give the electronic structure of neon in your answer. It's 2 marks, so you've got to say why it's unreactive, and you've got to give the electronic structure. So the electronic structure is 2,8. I've decided to draw it, 2,8. So that would get me the same mark as that. Okay. It's got a stable arrangement of electrons. Sorry, that's 1 mark. It's got a stable arrangement of electrons, or you can say it's got a full outer shell, or you can say it's got an octet or 8 electrons in the outer shell. Either one of those 3 will get you the 2nd mark. And if you've drawn this structure correctly, you will probably, can't swear to it, but you probably get a 2nd mark for showing that there's 8 electrons in that outer shell. So you've got the 2,8 and you've got 8 electrons in the outer shell. Usually it requires, when it says explain, it usually requires a because or a so statement. 4.6, how many atoms are there in 1 gram of argon? Well, we know that 1 mole is equal to 6.02 times 10 to the 23, because it tells us here. Okay, so we need to work out moles. Moles is grams divided by molecular mass. So Mr. Mass moles if you want to do a triangle, but the number of moles is grams divided by molecular mass. So if we know that 1 mole is that many particles, we just need to work out what fraction of a mole 1 gram is. So 1 of argon is a mass of 40, it's given us that, so grams is 1, molecular mass is 40, so 1 over 40 gives us the number of moles that we have, times 6.02 times 10 to the 23. Stick it into your calculator and you should come out with 1.51 times 10 to the 22. These are worth learning and doing a number of times. So you might do it once and think, I haven't got a clue. Do it a few times. Choose, instead of 2 grams, choose 20 grams or choose 100 grams and see what you get. Okay, but just practice these. Nice, easy 2 marks to get. So it'd be a mark for that and then a mark for that. Okay. So question number 5, it's all about electrolysis. Okay, some metals are extracted from molten compounds using electrolysis. Why? Well, usually because they can't be extracted using carbon, or they're more reactive than carbon. So you would say the metal is more reactive than carbon, that would get you a mark. Or you can say the metal is too reactive to be extracted by carbon, that would get you the mark, either one of those two. We're looking at the electrolysis of a molten mixture of aluminium. So what 2 substances does the molten mixture contain? So this is, do we know the aluminium extraction process? So we've got aluminium oxide and we have cryolite. Now cryolite's a little bit of an impurity that's used because it will reduce the temperature at which aluminium oxide melts. So it means you don't have to put so much energy into the process, so it's going to be cheaper in terms of cost because you don't need as much energy. So cryolite, and we're going to use aluminium oxide. 5.3, copper and chlorine are produced. So we know we're going to get copper and we know we're going to get chlorine from when molten copper chloride is electrolyzed. Complete the half equations. So if we start off with our copper ion, we are going to get copper. So we're going to get copper. So Cu2 plus gives us copper. We need to add 2 electrons to the copper to make this copper 2 plus ion neutral. So we've got 2 pluses there, 2 minuses there, they'll come together and we'll get a neutral copper atom. The other product we get is chlorine, and we need to know or remember that chlorine is a diatomic structure, so Cl2. So in here we've got chloride ions going to chlorine. We've got 2 electrons here that we are going to lose. So here's our chlorine and there's the electron that each chlorine has lost. So we've got 1 electron per chlorine, and there's the 2 electrons. Okay, so that's what I was looking for. Figure 4 shows the apparatus that a student used to collect to electrolyze copper chloride solution. So if he's so it's a solution, so we know it's aqueous. So we're definitely going to get copper, and if it's an aqueous solution, we possibly will get, we need to know what we're going to get if we electrolyze this. But let's look at the question first. The student measured the mass of copper deposited on the negative electrode after 60 minutes. Compare the mass deposited, the student compared the mass deposited with the expected value. So they're expecting, say, 10 grams. Did they get 10 grams, or did they get 6, or did they get 12? So it suggests 2 reasons why the mass deposited was different from the expected value. So was it too high or too low? Why would it be too high? Why would it be too low? So possibly the concentration or even the volume of the solution was different. So it wasn't what they were expecting. So the concentrations were different. maybe there were impurities in the solution. So you're not getting as much as you think because there's impurities. You might not have timed it for 60 minutes. You might have timed it for 59 minutes or 63 minutes. So there might have been some error in the timing. So longer or shorter. It's possible that so much copper was formed that some of it fell off the electrode. So when you weighed the electrode, there appears to be less than you were expecting. Or because you're using this power supply, maybe the voltage or even the current setting was not what you anticipated. It might have been different. So you might have wanted it set at 12 volts and it was set at 15 volts, or it was set at 8 volts. So it would give a different electrical throughput, and so you would get a different mass of copper. So any two of those would get you the 2 marks. These are worth, if you didn't get it, these are worth making a note of and learning. Put them on a flashcard, because these are experimental procedures and experimental anomalies that they can ask you about. Okay. Looking at 5.5 then, we've got an expected mass of copper we're producing copper over time, and every minute or 2 minutes or whatever we're making a measurement, and here we've got a graph. So over 30, I think it's 34 minutes, we gathered 6 milligrams of copper. It says determine the expected mass of copper after 24 hours. So it's really, what's the easiest way to read this table? And I thought to myself, well, 30 minutes is easy to read, because how many 30 minutes are in 24 hours? Well, 48 30 minutes are in 24 hours. So it wants 24 hours. So that's what I did here. So there's 48 half an hours in 24 hours. And so how much material did I produce after 30 minutes? And I read it off here, and I thought it was about 5.5. So I've said 30 minutes gives 5.5 milligrams of copper. So 48 lots of half an hour is 24 hours. So 48 times 5.5 gives me 268 milligrams. So that's my answer. So because I read 5.5, it's within tolerance. It was 30 minutes and I got 268. So that was my 3 marks. The mark scheme said that this was 5.4 milligrams, but there is a range. So if you chose 5.4 and then did this calculation, the result came out at 259, and again you would have got all 3 marks. So whatever, as long as it's within a very small tolerance here, the value, then you would get the marks for that. But you have to read the table, the graph. Okay, so let's have a look at the next bit. So silver nitrate solution was electrolyzed. They're really going to town on electrolysis here, and here we can see the change in mass of the negative electrode over 10 hours. So we've had to start a little bit higher up, so it's not 0. We've started, the mass of the electrode already has a mass, and then here we can see the additional mass that it's got. So it wants you to determine the mass of the negative electrode at the start. So we have to read that start, and you have to work out the scale. So now we're ramping up the difficulty now. So this is where the higher tier starts to kick in. We know we've got 10 small squares for 5 grams. So 10 squares is 5 grams. So 1 square is half a gram. So you can work out half, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, and then that's halfway up that between the last square. Actually, it's 9.5 squares. So 9.5 times 0.5 is 4.75 grams. But you can work it out that that's 4.5, and then half of a half is 0.25, so 4.75. So you can work it out. So 4.75. And then it says calculate the gradient. So we need the height here. So we're going to have a difference between the start and then this upper value. So that would give us the rise. And we need to work out the time. Well, the time's easy because it's from 0 to 10. So the change in the y-axis here is the difference between the top and the bottom. So 6.75 take away 4.75 is 2.0 grams. And I'm putting the grams in for a reason. And the change in the x-axis here is 0 and 10. So 10 take away 0 is 10 hours. So the gradient is 2 grams over 10 hours, which is 0.2. So the gradient is 0.2. It wants the units. Well, the units are grams divided by hours. So grams per hour. That's how we work out the units. Grams per hour. If you're not sure, go back through this again. Okay, question 6. Sodium reacts with chlorine. I immediately think sodium, group 1, Na+. It'll lose 1 electron, so it becomes Na+. Chlorine, group 7, it's going to gain 1 electron. It's going to become Cl-. Chlorine is Cl2. That's even before I look at this question. So now, what does it say? What is the balanced equation for the reaction? So I know sodium is reacting with chlorine. So chlorine is Cl2. So which ones of these have Cl2 in them? That one and that one. Okay. It makes sodium chloride, so Na plus Cl minus. So the formula is going to be NaCl, because that's a plus and that's a minus, and the salt itself is neutrally charged. So which one of these has NaCl? Well, that's NaCl2, so it's not that one. That's Na2Cl, so it's not that one. That's NaCl, that's NaCl, but this doesn't have Cl2, so it's not that one. No, it's not that one either. So it has to be this. Is that balanced? So Cl2, we need 2 sodium chlorides. And if we've got 2 sodium chlorides, we need 2 sodiums. Yes, so it's that one. By a process of elimination, you can work out which is the correct formula, okay, if you're not sure. So do use a process of elimination. 6.2. Hot sodium is put in a gas jar. Describe the observations. What do you see? Basically, if you were looking at the gas jar, it's got sodium in there and it's got chlorine gas in there. What are you going to see? So before the reaction, what will you see? Well, you'll see silver metal or solid, silver solid or grey solid, because that's the sodium. So you'll see a solid, a silver solid, and you'll see the gas in there. Chlorine gas is green or possibly yellow. So you'd see silver solid and green gas, which is the chlorine gas. Okay, when this reacts, what happens? Well, you're going to get a bright light. It's going to be, you need to know that sodium burns with a yellow flame or an orange flame. So you'd see a bright orange flame or a bright yellow flame. You would see white smoke, or you'd see the green colour will fade as it reacts. So after the reaction, all you'll see after the reaction is sodium chloride, which is a white solid. So you'll see a white solid or a white powder. So it's what do you see? What are the observations? So this is colours, solids, liquids, gases, powders. That's what it's looking for. Did you see a flame? If you did, what colour was it? Nice little 3 marks. Proved a little bit out. I think people read that and didn't answer it correctly. They answered a different question to the one that was there. So observations, what did you see? Solids, liquids, gases, colours. Okay. 6.3 then. Explain why sodium is less reactive than potassium. So you can say sodium is above potassium in group 1. So because you are having to do a comparison, you need to use lesser, fewer, more than, greater than. You need to use those comparative words. So sodium has fewer energy levels than potassium. Sodium's electrons are closer to the attractive force of the nucleus, so they're harder to remove than potassium. And there you've got 1, 2, you've actually got 3 marks there. You could say, so the attractive force is greater in sodium than potassium on the outer electrons. That's because the sodium electrons are closer to the nucleus. So the outer electrons in sodium are less easily lost than potassium. Okay, maybe I'd better put that than potassium. So it's 4 marks, so you need 4 facts, 4 different facts, okay? And I think I've got probably 5 facts there. 1, 2, 3, 4, 5. So maybe that will help you. Remember, anything to do with chemical reactions is electrons being lost. Okay, it looks like these 6-mark questions are usually levelled at level 1 and level 2 now. There used to be 3 levels, level 1, level 2 and level 3, but they're now only 2 levels. And you can answer these just by bullet points. You don't need swathes of sentences. So it says chlorine reacts with sodium and with hydrogen. Oh, sorry, chlorine reacts with sodium and with hydrogen. Compare the structure and bonding. Structure is one thing, bonding is another, in sodium chloride and hydrogen chloride. So I know sodium chloride is NaCl and I know hydrogen chloride is HCl. So I've drawn, to help me, the covalent HCl, and I've shown where the electrons are, and I've drawn the ionic sodium chloride. Okay, so now if I look at the bonding, let me treat the bonding first, then I can look at the structure. So what are the differences? You can literally list these. So we've got here, it's covalent bonding, whereas in NaCl it's ionic. We've got non-metal and non-metal in HCl, but it's metal and non-metal in NaCl. In HCl we share a pair of electrons, but in NaCl we transfer electrons. HCl is a molecule, whereas NaCl is ions, Na plus Cl minus. HCl has no charge, whereas NaCl is made of charged particles, albeit the overall charge is neutral. That's the differences. So what are the similarities? Well, both of these structures, the elements have full shells. So hydrogen has a full shell and chlorine has a full shell because they share, and sodium ion has a full shell because it's given its 1 electron away, and chlorine has a full shell because it's taken it. So the similarities are that they've both got full shells, full outer shells. The other similarity is that we use electrons in the bonds, or the electrons move to create electrostatic forces. We've got strong bonds. Both the chlorine covalent bonds are very strong, and in sodium chloride the electrostatic forces are very strong. So that's the bonding. So we can see the similarities and the differences. Okay, so it says compare. So let me go up here. It says compare. So similarities and differences, pros and cons, however we do this. So similarities and differences in bonding. Let's look at the similarities and differences in structure. Okay, so the structure is how the molecules arrange themselves, or how the ions arrange themselves. So in HCl we've got simple molecules, whereas in NaCl it's a giant lattice structure. In hydrogen chloride we've got intermolecular forces between the molecules which are fairly weak, which is why they're simple molecules and they're usually gaseous. Whereas in sodium chloride we've got strong electrostatic forces, which means they're usually solid. Okay. HCl, it's an irregular structure, you've got random motion, Whereas NaCl, because they're strong electrostatic forces and it's a giant lattice, it's got a regular structure and all the ions are in fixed positions. They're the differences. If we look at the similarities is we've got forces of attraction in the structure. So forces of attraction, that's between molecules, and here we've got forces of attraction electrostatic, and that's between ions. Okay, but that whole thing is a little bit of a brainstorm really, and that would get you the full 6 marks, even if you missed, say, the similarities off at the bottom. Just a number of these, a couple of these differences and a couple of them in similarities would get you more marks. It says level 2, you have to have a comparison of structure and a comparison of bonding. So just a couple of points for the bonding and a couple of points with the structure would get you into level 2. So that would get you 4 marks straight away, and then obviously the amount that you put on there would take you up to 5 or 6. The idea is you want to be getting at least 5 marks on these, so get as much as you can. Okay, so at any point you can go back through the video. If you're still not sure about the explanation, don't be afraid to email either myself or Miss Priest. Tell us which question it is and what part you don't understand. Okay, so I hope this helps you to review your mock paper, and that you take away quite a bit of information, not just on the knowledge, but also on exam technique.